Hey everyone, this is Aman Soni and welcome to M12. So this is a complete series of the deep learning and its practical implementation. And in the previous part, we have covered the perceptron, and also we have seen what the weight and the bias looks like and what are their role in the neural networks. Okay, so we have also covered the glimpse of the backward propagation in the previous video, right? So in this part we are going to be seeing that in detail, and there's a problem associated with the weight updation, that's called the vanishing gradient problem, right? So we are going to be seeing that as well. So let's get started. Let's start where we left off in our previous video. And everyone knows this is a perceptron, right? So what we have here, we have some certain inputs and some weights associated to it, right? Then after that, these inputs and weights are passed into the summation function, where the inputs and weights get multiplied, and all of them get a addition product. Okay. Then after that, after doing the addition, we get our bias introduced. Okay. Then after that, this function gives the output to the activation function. Okay. Then after that, according to the type of activation function, it will give some certain output that will be our predicted value. Okay. So this is all about the perceptron. So let's suppose we have a data set. Okay, and there are some certain features associated to that data set, right? And in corresponding to those features, there are some certain data values. Okay, and those values are passed into our perceptron model. Okay, so our model is giving a predicted output of uh, zero, you can say. Okay, so but ideally in this case, our actual output is one, right? So this is an issue, right? So in order to deal with this kind of issue, we have a loss function. Loss is equals to y minus y hat. Well, there are some certain different kind of loss functions, but for the sake of simplicity, we are taking this one. Okay, so it is nothing but the difference between the predicted value and the actual value, right? So we are taking this loss function. Then after that, we have to minimize this loss function, in order to have the better accuracy of our model, right? So to have a better accuracy of our model, what we can do here, like we can back propagate and change our weights, right? Initially, the weights were assigned to as the random values, right? Like we didn't have the knowledge like what ideally we should take the weights, right? So in order to deal with that, we back propagate and we update our weights, right? And in order to do that, we use some certain optimizers. Okay. So what is the use of the optimizers? Optimizers are nothing but the techniques used to minimize the loss function or boost up the accuracy. Okay. So you might have heard the gradient descent GD, and that's a very commonly used optimization algorithm. And in this scenario, we'll also use that. Okay, so I'm going to make a separate video on the gradient descent and the learning rate. So what is the forward propagation? Like we got some features, then we assigned some certain weights to it, and then we use the summation function, and then we pass that into the activation function. And after that, we got our output, right? And what is back propagation? After getting the output, we calculated our loss, and after that, we use optimization algorithms like the gradient descent in order to uh, update our weights. Okay, so that's called the back propagation, and after that, the cycle goes on, and we propagate forward, right? So eventually, what we are going to get, like we are going to reduce this loss function, and we are going to get the high accuracy of our model, and we are going to get the desired results from our perceptron model. So since we know the basics of the forward and the backward propagation in the deep learning, let us further continue our discussion over the backward propagation. Okay, so there are two main topics in the backward propagation. The first one is the weight updation, and the second one is the chain rule of differentiation. Okay, so let us start from the weight updation itself. So what does it say? Like W new is equals to W old. That means the new or the updated weights will be equal to the previous weights minus the learning rate into the partial derivative of loss with respect to its weight. Okay, so the partial derivative is nothing but the slope itself, right? We have seen in the previous classes as well. Okay, so W new is equals to W old minus the learning rate into the partial derivative of loss with respect to weights. Okay, so what is the learning rate here? For the sake of simplicity, let me take the value to be 0.01. Okay, so well, there are some different kind of techniques used to set these learning rates, but for the sake of simplicity, right now, let me take it 0.01. Okay, for the instance. Then after that, let us plot this on the graph. Like it is the loss, and in the denominator we have the weight. Okay, so loss is in the y-axis, and the weight values are on the x-axis. Okay, so we all know in order to boost up our accuracy, in order to increase our accuracy, we have to minimize the loss function, right? So this is how our loss function looks like, and we have to minimize it. Okay, so this is going to be the optimal solution for our algorithm. So let us consider two scenarios here. Like in the scenario one, we are situated on the left side of the optimal solution, and in the scenario two, we are on the right side of our optimal solution. Okay, so let me calculate the gradient for scenario one and scenario two. Okay, so for the scenario one, like we can clearly see the derivative is going to be negative because it is making the obtuse angle with the x-axis, right? So if it is making the acute angle, it will be positive. Okay, so in this case, we are making an sorry, the tangent will be making the obtuse angle with the x-axis. Okay, so the graph is going to be negative. Okay, then after that, in the scenario 2, it is making the acute angle with the x-axis, so the gradient is going to be the positive one. Okay, so if the slope is negative, like we all know, the partial derivative of something over something is the slope itself, right? So that means if the derivative is negative, that means the slope is negative. Okay, so if the slope is negative, let me calculate the weight updation formula for you. Okay, so what was the formula for the weight calculation? W new is equals to W old minus the learning rate into the gradient. That means the partial derivative of the loss function with respect to the weights, right? So in our scenario, where the slope is positive, that means this value is positive. Sorry, this value is negative, and we are having a positive value that is 0.01 of the learning rate, right? So the product of negative and negative is eventually going to become the positive, right? So in this scenario, what our weight updation formula is going to look like: W new is equals to W old plus some XYZ value, right? So let us see that in graph. Okay, so in the scenario one, where we have the negative graph, we are having the value of weight somewhat like that is lying here, right? Okay, then after that, we know that the W new is going to be incremented by some value, right? So the value is going to be more than its previous value. Like we are having its value here, and according to that mathematical equation, the value is going to lie here after this approach. Okay, then after that, our loss function the value of the loss function will decrement, right? So that means it is approaching towards the optimal solution from the left hand side, right? Similarly, in the positive, when the slope is positive, the W new, sorry, W new is equals to W old minus N, that is positive, and the slope which is also positive. That means it is going to decrement by some value. Okay. In the scenario 2, our value lies here, and we have some certain weights attached to it. Okay. So the weight is going to get decremented in order to achieve the state where the loss function is, where the value of the loss function is very low, right? So it is approaching towards that point from its right direction. Okay, so yeah, this is the back propagation, and this is the weight updation formula for the positive and the negative slope. So you have to learn this weight updation formula, and you can derive the result of whatever scenario you want. Okay, so W new is equals to W old minus the learning rate into the uh, partial derivative of loss function with respect to its weight. Okay, and not only in the case of weight updation, in case of bias updation as well. Okay, so the W new is equals to W old minus the learning rate into the partial derivative of loss function with respect to its weight, that is WO. Okay, so this is going to be uh, the bias updation formula as well. Okay, so you have to learn this expression in order to solve the question for the weight updation and the bias updation as well. Okay, so let us now continue our discussion on the chain rule of differentiation. Okay, so let's suppose we are having a neural network with a single hidden layer. Okay, so there are some inputs associated to these, like here the x1, then comes the x2, and then comes the x3. Okay, then after that, we know there will be some different weights associated to these inputs as well. Okay, so W1, W2, and there comes the W3. Okay, so this is a summation layer. Okay, then what it is having, it will be having a bias associated to it. Okay, let me put B1 here. Okay, then after that, it will be giving a certain output from this summation function. Okay, so let's suppose it is O1. Then after that, the O1 is also associated with a weight, that is W4. Okay, then it is passed to the sigmoid function, or you can say the activation function. Okay, then after processing the input taken and the weight associated to it, it will give some output. Let's suppose that output is O2. Okay, and we are having a bias updation here as well. That is V2. So while updating the weights, or you can say uh, while propagating in the backward direction, let's suppose we have to update the weight for W4. Okay, so what was the formula for the weight updation? W4 is W4 new is equals to W4 old minus the learning rate into the partial derivative of loss function with respect to the weight of W4, that is old, right? Okay. So in case when we have to update the weight for W4, we use this. Okay. We have used this function. We have used this, what can I say? Yeah, formula to update the weights. But what if we have to update the weight for W1? Okay. So let me write it for you. Yeah. W1 new is equals to W1 old minus the learning rate into uh, now tell me, can I write this partial derivative like this, like WH upon uh, O2 into partial derivative of O2 with respect to partial derivative of O1. Then after that, I can write partial derivative of O1 with respect to partial derivative of W1. Okay, so now let me try to make you comfortable with this expression what I have written here. Okay, so what we had to write initially, like W1 new is equals to W1 old minus learning rate into partial derivative of the loss function with respect to W1, right? So don't you think eventually this is going to become this only, right? So partial derivative of O2 and O2 cancels here and O1 and O1 cancels here, and eventually this is going to become this only, right? So how I wrote this function like in this manner. Okay, so first thing you have to see how many outcome values are you having from specific functions. Okay, so let's suppose if you had to update the value of w2. Okay, so while propagating in the backward direction, the first output you are getting is w2. Okay, so w weight updation is dependent on o2, right? Then after that, going in the previous direction, what else output you received was O2, O1, sorry. Okay, the first one was O2, then after that was O1. Then after that comes the weight updation, the weight part. Okay, so let me write it for W3. Okay, so W3, for your understanding, like W3 is equals to W new is equals to W3 old. Like pause the video and you can try it yourself as well. Minus learning rate into, okay, so we have to write it like the partial derivative of h upon partial upon w, like we are calculating for w3, so here lies the w3. Okay, so now how you can write uh, in terms of chain rule of differentiation. Okay, so let me write it for you. We have to write the loss function here, right? Then after that, while propagating in the backward direction, the first output we received here was with respect to O2. We'll after that we'll multiply partial derivative of O2 with respect of with respect to O1, right? Then comes the O1. Then after that, partial derivative of O1 with respect to W3 only. W3. Okay. So this is what the chain rule of differentiation says. Okay, and not only in this case, like in the bias updation as well. Like if we are updating the weights, okay, so let's suppose हमने यहाँ से हमारे सारे के सारे हमने इनपुट्स लिए, okay, so forward propagate होके we got some values, okay, then after that we have to back propagate and choose the value of weights that are more suitable for our model, and we are minimizing our loss function from it, right? That means we are boosting the accuracy. Okay, so first thing, like for the weight updation of W1, we have to go through the O2, O1, and then comes the W1. Okay, similarly in the case of W2 and similarly in the case of W3. And this is how we denote the chain rule of derivative in the case of weight updation. Since we have seen a example for the chain rule of differentiation in the weight updation, why don't you do this problem? Like we have to calculate the weight of W1, or we have to update the W1. Okay, so yeah, let's start. By the way, for your better understanding or learning purpose, you can pause the video and try it yourself as well. Okay, so yeah, let me do it now. How to do that for W1? So, what was the weight updation formula? W new is equals to W old minus learning rate into the gradient of the or the partial derivative of the loss function with respect to the weights, right? Now, yeah, let me take the green color. Okay, so for W1 new is equals to W1 old minus the learning rate. Then after that, uh, the weight depends upon the first thing it is depending upon is the output number O31. Okay, that means the partial derivative of the loss function with respect to the output of O31. Okay, then after that we know यहाँ पे O31 आया and we have to cancel that out, right? So यहाँ पे हम partial derivative of O31 तो लेंगे ही लेंगे. Then after that tell me ये और किस output के ऊपर depend कर रहा है? Okay, so now we have two ways. Like we can go in this direction as well, and we can propagate from this direction as well. Okay, so let me take the first direction for you. Okay, so yeah, we have taken the partial derivative of O3, and then it is depending upon the outcome of O21. Okay, and after that comes the O21. Okay, now you know we have written O21 here, and we have to cancel that out. And after that, we'll take O21 here, and what comes next? Then comes the O1. Okay, partial derivative with respect to O1. Okay, and now since we have written O1 here, so partial derivative of O1 with respect to what else is there? Nothing. Like we have to calculate for W1. Okay, W1. I have done some mistake here. Okay, so we have to calculate for this one, right? So with respect to W1, right? So you can see here, like ये सब cancel होके eventually, like let me do it for you. Like ये सब eventually cancel होके बचा तो यही partial derivative of what was that loss function with respect to the uh, old weight, right? Lekin we have to approach our problems in this manner, or the CPU, or we can say our machine approaches the problem in this manner. We can update our weights like that. But you will say, why did I selected the first one? I could have gone with the second one as well, right? So let me write the second one. Like यहाँ तक तो we have the same equation, right? Minus learning rate into upon O31. Then after that, O31 upon uh, O22. After that, partial derivative of O respect to partial derivative of O1. After that, O1 plus partial derivative of W1, right? So this could be our answer as well. But I'll say not only this is our answer, and this is also not our only answer. Our answer is the OR product. Oh, sorry, the or you can say the plus of these both, the addition of these both uh, expressions. Okay. So now we have covered the chain rule of differentiation as well, and let us now further take our discussion on the vanishing gradient problem. Okay, so let us consider we are having this multiple layer neurons. Okay, multiple layer neural network. So it is our hidden layer 1 and hidden layer 2, hidden layer 3, hidden layer 4, and it is the hidden layer 5. Okay, and all of them are having the sigmoid function as their activation function. Okay, and we have propagated in the front direction, and now we have to update our weights. Okay, so this is the W1 and we have to update the W1. Okay, so let me write the expression, or you can write it by yourself as well. Now I think you are capable to do that, right? So yeah, W new, that is, we are writing for 1. Okay, so W new is equals to W old minus the learning rate into, uh, I'll directly write in the form of the partial derivative. Okay, so the partial derivative of loss function is to 5 1, then 5 1, 4 1, 4 1 upon 3 1, that 3. Okay, so partial derivative is also associated to all those. Okay, so you can write that O31 and O21, then comes the partial derivative of O21 with respect to O11. Sorry, after O22 is written wrong there. It is O21. Okay, then after O21, here comes the partial derivative of OW1. Is this OW1? Okay, so this is our weight updation formula. Okay, so now you can easily see from this formula, like in the sigmoid function. Let me make a graph for it. This is a sigmoid function, right? This is zero point 0.5, and our values, uh, this graph is like this, right? It have its saturation point after this, and it has its negative saturation point like this. Okay. Do you know, like, if we take the derivative of the sigmoid function, it can only touch the mark of 0.25 only. The derivative of the sigmoid function looks like this. Okay. So the maximum value here is 0.25. Okay. So our partial derivative looks like this. Sorry, partial derivative of the loss function with respect to OW. It looks like this, right? सो यू नो दैट कि हमारी हर लेयर के अंदर हमारे पास सिग्मॉइड फंक्शन है, ठीक है, एंड द मैक्सिमम वैल्यू वी कैन अचीव इन अ सिग्मॉइड फंक्शन इज लाइक 0.25. So let's suppose, to be on a safer side, let's suppose we take the first value of this one to be 0.25. Okay, or you can say the first value to be of this one 0.25. Then after that, it is going through multiple sigmoid layers, right? Then after that, the maximum value we have taken is 0.25, and we know कि वैल्यू इससे रेगुलर ऑर्डर में कम ही होगी. रीजन बीइंग, हर लेयर के ऊपर एक एक सिग्मॉइड फंक्शन लग रहा है, राइट? तो एक सिग्मॉइड फंक्शन के पार्शियल डेरिवेटिव का रिजल्ट अगर 0.25 आ रहा है, देन आफ्टर दैट उस फंक्शन के नेक्स्ट लेयर पे हम जब जा रहे हैं, वी आर नॉट गोइंग टू रिसीव अमाउंट दैट इज मोर देन 0.25, राइट? सो in the next part, 0.25, then let's suppose we have 0.15, then 0.10, and then 0.05, and then after that comes the 0.02. Okay, so now you can see like it is clearly decreasing, right? So eventually, when you are multiplying the small number with more smaller number, and the process goes on repeating, what will happen? Like, it is going to be uh, turned out to be a very small number, right? It is very small. Then after that, the learning rate into the small number is also going to be a very small number. Reason being, uh, generally we take the learning rate in the range of zero point 0.1 to 0.001, right? So if we are multiplying a small number with also a small number, what it is going to give? A very, very small number, right? So if we put that into our weight updation formula, Here it is, right? So W new is equals to W old minus, this is a very small number. Okay. So if you are subtracting a very, very small number from something, I don't think so it will give any kind of like difference. There won't be any kind of difference in it, right? So the difference between the W2 and W1 will be like negligible. Yeah, whatsoever. Spelling mistakes are terrible. You know that, right? Then after that, the difference between these two are like negligible. So what does that mean? That means like the W new is almost as same as the W old. Like the new values aren't that much changed, right? So it is somewhat similar to W old. That means even when you back propagate, your weights are not getting updated, right? So that is nothing but the vanishing gradient. So this is a problem, and to deal with that, we have some different kind of activation functions. Okay, so activation functions. Okay, and we are going to see about the activation functions in our later video. But for now, like we have seen the sigmoid, and there are some limitations associated to sigmoid function. So to deal with that, we have to come with some different kind of activation functions. And let me give some names if you want to like learn prior. First one is the tan h, then comes the ReLU, then comes the leaky ReLU, and then comes the uh, pre-ReLU, or you can say the parametric ReLU, or then comes the softmax. The list goes on and on, by the way, but these are the important ones. Like these are the most commonly used activation functions. Okay, so in today's video, we have covered the back propagation and vanishing gradient problem, right? So while dealing with the vanishing gradient problem, we have to learn some certain activation functions to deal with that. And in the backward propagation, we have seen the chain rule of differentiation, and we have seen the weight updation formula, weight or bias updation formula, you can say, right? See you in the next video, and thank you. Happy learning. Bye bye.